So now let's talk about how we can use Monte Carlo estimation to estimate the MSE of a statistic or an estimator. So last time we talked about a common measure of estimator efficiency, the mean squared error, or the MSE. So to recap this, well, you're taking a test next week, so it's good to have some reviews. The MSE of theta hat is given by the expectation of the square distance between theta hat and the true theta. And we mentioned that the smaller the MSE, the smaller the expected difference between your estimator and the true value, and the better or the more efficient your estimator is. So the Monte Carlo integral estimator we talked about earlier in Monte Carlo integration was a specific kind of estimator. For any general estimators, say theta hat, how do we get its MSE? So let's see an example. So the idea of the implementation is actually very similar to before. So let's just see an example. This example concerns the trimmed mean. So suppose that we collect a random sample of size n from the distribution x. We might want to use these samples to estimate the mean of x, in other words, the expectation of x. But how can we do that? An obvious choice of such an estimator will be the sample mean. So we can say in this case theta hat, which is the estimator for our unknown mean of the distribution, is equal to x bar, which is just the sum of all the samples divided by sample size n. There's an alternative to this, which is the trimmed mean. So what is the trimmed mean? So now we have n random samples. So if we sort all random samples, x1 all the way up to xn, from lowest to highest, in other words, we get x parentheses 1, x parentheses 2, etc., where 1 is less than or equal to the second, etc., all the way until the largest. Then the kth level trimmed mean is given by x bar minus k. Here's the notation for the kth level trimmed mean, which is equal to 1 divided by n minus 2k, and the sum of all the xi values, not from 1 to n, but instead from k plus 1 to n minus k. So what exactly is it doing here? It essentially is saying I sort all of the random samples I get. I get rid of the top k and the bottom k. And then using the middle guys that are remaining, I calculate the sample mean. So we're trimming the two counts. You can see that the median is an extreme case for the trimmed mean, where you are left with only 1 or 2 observations in the middle. So it's 1 if your n is odd, and it's 2 if your sample size n is even. And you calculate the mean of the middle guys. The untrimmed mean is the other extreme where k is equal to 0, meaning that we're trimming nothing on the left and the right tails. And we're just calculating the sample mean. So one thing we might be interested in is comparing the efficiency of the trimmed and the untrimmed mean under various sorts of possible scenarios. On one hand, if our distribution is heavy-tailed, so something like Cauchy, or it is somehow contaminated by some extreme values or outliers, then the sample mean might not be very robust. On the other hand, trimming implies that we are getting rid of some of our samples, so it's reducing our sample size. So this can also lead to a decrease in efficiency. In other words, an increase in variance, because we have a lower sample size by getting rid of some of the observations at the bottom and the top. So you can see it's not that straightforward. So when exactly is the trim mean more efficient, and when exactly is the untrimmed mean more efficient? Well, one thing you might try to approach is analytically deriving the MSE. However, this will be really hard because the trim mean involves the convolution of the k plus 1 to the n minus kth order statistics. So you might really don't want to do this by hand. So what we can do is to resort to Monte Carlo techniques. And here we will conduct a mini simulation study where we numerically approximate the MSE of the two estimators under different scenarios. Okay, so we have a simulation study. So you'll see the simulation study word a lot if you do a lot of Monte Carlo related tasks. So it's essentially saying that we can use Monte Carlo techniques to numerically or statistically approximate some parameters or statistics we are interested in. So let's suppose that our distribution X is a mixture of normal 0, 1 and normal 0, 100. So here the standard deviation is 10. In other words, so we have learned about mixture distributions when we talked about random variable generation. The PDF of X is given by P, a probability between 0 and 1, times the normal density for standard normal, plus 1 minus P, which is the proportion associated with this distribution, times the corresponding density when the SD is equal to 10. So in other words, an observation comes from normal 0, 1 with probability P, and it comes from normal 0, 10 squared, which has much larger variance with probability 1 minus P. You can see that here, the P, which is the probability that something comes from normal 0, 1, will determine how much contamination we should expect in our data set. If P is equal to 1, that would mean that all of the samples will come from normal 0, 1. However, if P is not 1, say P is, say, 0.9, that means that 10% of the observations will come from normal 0, 10 squared. And that will bring us a lot of extreme values. It isn't hard to see that the theoretical mean of theta, so the theoretical mean of this distribution, the mixture of two normals, both with mean 0, is actually also 0. So we know that theta, the true theta, is equal to 0 in this case. So suppose that every time we draw a sample from this distribution of size 20, so the sample size n is 20. Let's see how the efficiency of our trimmed mean x bar of minus k changes when we vary two things. The first is when we play with the proportion or the probability that a sample comes from normal 0, 1. So this will be 1 when there's no contamination, 0.95 where there is 5% contamination, or 0.90 when there is 10% contamination coming from the distribution with the larger variance. So we'll try these three different possible p-values. We will also try different case, that is the level of trimming we want to do to calculate x bar. Because our sample size is 20, we'll try all possible cases between 0 and 9. 0 corresponds to the case where we are not getting rid of any of the 20 samples. So we just calculate the untrimmed mean. So k equals 0 corresponds to the traditional x bar. And then k equals 9 corresponds to the case we are trimming the top 9 and the bottom 9. And we are just calculating the mean of the middle two samples. And that's our median, actually. So let's see how the MSE of x bar negative k changes with these two factors. Oops. All right, so since the MSE of theta hat, it's the x bar in this case, is in general given by the expectation of theta hat minus theta squared. You can see that we can estimate it by drawing m samples of theta hat minus theta squared, and then computing the sample mean of these m samples. So here we know that our true theta is 0, and our theta hat, the estimator, is the trimmed mean, K-th level trimmed mean. So like before, we will first need to draw random samples of x's. So what are our x's? Our x's come from that mixture distribution, and we're playing with the possible p-value. And we learned how to draw from the mixture distribution in week 2. We will first need to draw the group membership for each individual. So for each possible sample. So we draw for all of the 20 samples, delta, which follows the Bernoulli distribution with probability p. If you get a 1, it indicates that this person comes from the normal 0, 1 group. And if it's equal to 0, it means that this person comes from the normal 0, 10 group. And then in the second step, after drawing the group memberships, given the group membership, which is either 0 or 1, we will draw from the corresponding distribution. So either standard normal or the normal distribution with standard deviation of 10. So here's a function in R that implements this. This function is what I call sample mix, which is a function for drawing the mixture samples for the current problem. It takes 2 arguments, n and p, where n is our sample size. So in this case, we're using n equals 20. We're drawing 20 samples from this distribution. And p is the mixture probability. Like we said, we first draw the group membership, which is equal to 1 times r unit n less than p. So this is essentially doing the inverse transform sampling for a Bernoulli distributed random variable where there are just 2 possibilities, 0 or 1. So the group we end up with is going to be a length n vector. If the nth entry is equal to 0, that means that this sample will need to come from the normal 0, 10 distribution. If the corresponding group entry is equal to 1, it means that this person or this sample will need to come from the standard normal. Okay. So like before, we create a sigma vector of length 2, indicating the corresponding standard deviations of the 2 groups. So C, 10, and 1. And then we use vectorized operations and draw our samples, the 20 samples from X. By doing R norm, size is 20. The mean is going to be equal to 0 for both of these groups, so we don't need to play with that. For the standard deviation, this will depend on the group membership of this person. So we say that SD is equal to sigma's group plus 1th entry. So if a person's group is 0, group plus 1 will be equal to 1. So we will be looking at the first entry of sigma. So for individuals with group equals 0, we will be using the standard deviation of 10. For people who have group equals 1, we will look at the second entry of sigma when we draw their X. So we'll be using the standard deviation of 1. And the resulting X's will be returned, and that's going to be our length in samples from this mixture. So this is just a review of what we talked about 3 weeks ago. All right. So now we have our X's. Our next step is to compute theta hat minus theta squared using our X draws. In this case, we mentioned that this is given by theta hat bar minus k minus 0 squared, because true theta is 0 and this is our theta hat. And this is simply equal to theta bar of minus k, which is the trim mean squared. So before computing this, let's try to first make a function that computes trimmed means. I'll call this function t mean. So t mean stands for trimmed mean. And it's a function that takes the x, which is our random samples of size n, and k, which is the trim level at its inputs. And the function is actually quite easy. We sort our x's, and then we trim the corresponding entries at the top and the bottom, and calculate the mean of the remaining entries. So here, the first line of code, xs, denoting x sorted, will be the sort function applied to x. So what this sort function does is it will return a vector where x is sorted from the lowest to the largest. And then let's calculate the mean of the middle entries. So the entries of xx from the k plus 1 entry to length x, which is n minus k entry. And then we will return this mean of the middle entries. So subsequently, let's draw the x bar minus k under each condition. So each of the p conditions and k conditions. And we will use an m of 10,000 again and try to evaluate what is the MSE estimate using Monte Carlo estimation. So I will denote that by MSE hat, which is given by the sample mean of x bar k minus 0 squared. And also, what is the standard error estimate associated with MSE hat? So how much random fluctuation do we expect in our estimated MSEs? So here's a function that computes here's a function that returns the MSE and the standard error estimates given particular values of m, n, k, and p. There are 4 arguments of the function. M is the number of replications we want to do, so the number of the square distance draws we want to obtain. N is the sample size of our x's. K is the trim level from 0 to 9, and P is the mixture proportion, so how many samples come from normal 0, 1. This function is called trimmed MSE. So this function will make use of some of the earlier functions we have created. The first step is to create a all zero vector. So this all zero vector will be used to store all of the theta hats or the trim means we get, the k level trim means we get across the m replications. So for each j between 1 and m is here 100,000. We first use the sample mix function we created earlier to draw n samples from the mixture distribution where the mixture weight for the normal 0, 1 class is given by p. So now we end up with n samples from the mixture. Then we compute the corresponding theta hat. So the jth replication of theta hats, the jth entry of this vector, is going to be equal to the trim mean of the axis at the kth level. So when this loop is over, you will end up with a vector of length m, where each of the entries are the trim mean calculated from the corresponding samples. And then with these theta hats, which are the trim means, we'll be able to calculate the MSE estimation, the estimated MSE. So let's call it MSE at est. And like we said, this is given by the mean of the theta hats minus 0 squared. So that's going to be our estimated MSEs. To find the corresponding standard error, let's recall that this is given by the SD of theta hat minus x squares divided by the square root of m. So SE of MSN, it will be equal to SD of this thing divided by square root of m. And then in the end, we will return a vector where the first entry is MSE est, which is the estimated MSE, and the second entry is the corresponding standard error estimate. So Our question in the simulation study is how do P and K affect the MSE of our trim mean? Let's now loop over all possible P's and trim level K's and see how under each of the P and K combinations, how the MSE changes. So we will use, instead of using a for loop to do this, so you can see you can loop over all P's and loop over all K's, we will use a function called supply to replace the loop over all K's. So this is kind of similar to the apply function that we applied earlier to matrices. So when we wanted the columns standard deviations, we used the apply function and then apply the function SD to each of the columns of a matrix. This is what we did maybe in week 3 or week 4. The S apply function, which I believe stands for simplified apply function, is similar to apply, except that it applies a function, the argument called fun, to every element of a vector or a list instead of columns or rows of a matrix. So our possible values for k's are 0 to 9. So 0, 1, 2, 3, all the way up to 9. That's our trim levels. So that's a vector where we can use the supply function. Let's try to get the results for each of the possible p's. So p of 1, 0.95, and 0.9. So first, let's do it for p equals 1. So let's call our results p1. So this is going to be equal to the supply case from 0 to 9, the function trimmed MSE, which is the function we created earlier. And because we just want to apply it to the possible values of case, we have to specify the other arguments of the trimmed MSE functions. So let's say m is equal to 10,000, n is 20, and p is 1. The code is a little bit overflowing over here, but if you look at our markdown handouts, we'll be able to find the complete code. Essentially, you can see this part is just p equals 1, p equals 0.95, and p equals 0.9. So we say supply case trim MSE, meaning that we're going to apply the trim MSE function to each of the possible k values from 0 to 9. We do the same for p equals 0.95 and p equals 0.9. So what exactly are the results? So what are the outputs of the supply function? Well, results p1, which is the output of the supply function applied when p is equal to 1, and similarly results p2 and results p3 will each be a 2 by 10 matrix, where the first row is the MSE estimate. So that corresponds to actually the first entry that is returned from the trim MSE function. And then you can imagine that the second row of this 2 by 10 matrix will be the standard error estimate of the MSE estimates. So that's the second entry that is returned from the trim MSE functions. So the rows are MSE estimate and the corresponding standard error estimates. What about the columns? Because we applied the function to each of the possible k values, the 10 columns of this matrix will each correspond to a trim level k, which ranges from 0 to 9. So first column will be k equals 0, meaning that it's going to be the results on the MSE estimate and the corresponding standard error when k is equal to 0, so no trimming. And second is k equals 1, etc., all the way until the 10th column, which corresponds to k equals 9. So that's the structure of the results matrices. Let's give the rows and columns names so we can display it, and the display version will be prettier and we'll be able to look at it and understand the results. So we're going to use something called row names here applied to each of the matrices. So the row names of the 3 results matrices will be MSE and SE respectively. The column names will be k equals 0, k equals 1 all the way up to k equals 9. And now we can look at the results. So here are the results when all of the samples come from normal 0, 1. So that's a case when p is equal to 1 and none of the samples come from the larger variance distribution. So this result is stored in the results P1 matrix. Let's display it by rounding the results to 3 digits. And here is what the matrix looks like. You can see that it gives you the MSE of all of the possible k values. So it is again overflowing, but by looking at the trend, you get an idea. So when there is no contamination, you can see that the untrimmed mean, that is the case that k is equal to 0, will result in the lowest MSE. So in this case, MSE is equal to 0.05. And as we increase the trim level, we can see that the MSE keeps going up. So for the uncontaminated situation, the untrimmed mean will perform the best. How about when there is some degree of contamination in our data? So what if P is equal to 0.95 or 0.9? So here are the results for those two cases, where either 5% or 10% of there's either 5% or 10% chance that X comes from the normal distribution with standard deviation of 10. You can see that here the results is no longer the same as before. Specifically, when P is equal to 0.95, we can see that the untrimmed mean actually has really high MSE. It's around 0.3. The lowest MSE occurs when K is equal to either 3 or 4. And then afterwards, because we're trimming probably too much, the MSE will start to increase again. So the lowest MSE is achieved when K is equal to 3 or 4. And let's look at the case with even more contamination. So when P is equal to 0.9. You can see that here, again, the untrimmed one is not doing well at all. The lowest MSE occurs at K equals 4, where the corresponding MSE is around 0.07. So what does this tell us? It tells us that when our data does not contain a lot of extreme values, then the untrimmed mean, so when K is equal to 0, will have the lowest MSE, will be the most efficient. However, if our data contains some degree of contamination, then the trim mean with some middle range or a appropriate trim level will result in the lowest MSE. So this is a really simple example where we're just trying to conduct a mini Monte Carlo simulation study and see how the trim mean estimator with different Ks perform under different Ps. You might ask, how exactly is this useful in practice? Well, if you do a lot of statistics, either when you're trying to develop models, trying to develop new methods for estimators, or if you do things like machine learning, you will see MSE is very commonly used as an evaluation criteria of your methods or models. So in those cases, by conducting Monte Carlo simulation studies, it gives you a very convenient method that can be implemented to evaluate how exactly is your method performing under different kinds of scenarios.